will go ahead and get started. For anybody who's on Zoom at the moment, if you can understand me, they're going to sort out the audio as we go. The recording apparently is okay. So, sorry. It's our first seminar of the year. We're knocking the rocks out of the system here. So it's my great pleasure to introduce Tryphon Georgiou. He is currently down at UC Irvine, and have you been there your entire career?
No, it's just 7 years. I was
at
the University of Minnesota.
Oh, right, you were at Minnesota before that. Sorry, read the whole thing. Right. Yeah, I'm not going to quote the whole thing here, but so he did his basically his undergraduate education at the National Technical University of Athens in Greece, and then went to the University of Florida, Gainesville for his PhD. He is currently a distinguished professor at the Department of Mechanical and Aerospace Engineering at UC Irvine, also emeritus at University of Minnesota. Fellow of many organizations, IEEE, SIAM, which is Applied Mathematics, IFAC, which is International Federation of Automatic Control, AAAS, and a foreign member of the Royal Swedish Academy of Engineering Sciences. So what he's going to talk about today is, I'm going to go ahead and say the whole title. I'll give a little bit of context. So, Dissipation and Power in Physics and Biology, Optimal Mass Transport meets Stochastic Thermodynamics. Now, what he told me, if that was a little bit of a mouthful for some people to digest, is he's really going to focus a lot on the intuition. There will be the mathematics shown along the way, but you're going to really tie it all together for everyone. And then I also made a request for him, because we have a bunch of our professional master's students either listening in or they're going to listen in later, is to also, if you could, give a little bit of perspective on kind of how you run your group, your research group, balance your work-life situation, how you help train up our next generation of engineers. Just kind of your thoughts on that would be wonderful, because I'm making the MAE students think about that a lot this year. So I'm going to hand it over to you at this point, and
thank you very much, Christy.
Thank you for being here.
Thank you. It's a privilege being here. Thank you very much. It's a great department, and I truly enjoy my discussions with colleagues and students, learning a lot. Just to follow up on Christy's question, I consider myself very fortunate to be in academia. And I've enjoyed through the years my interactions with colleagues and students. The way I run my group and the way I interact with colleagues, it's like I try to have an open sort of forum of ideas. Academia is very much about exchange of ideas. We're all here sort of in some ways very selfish. We want to learn. And that's what we are being paid for. Learn and produce and be creative with following sometimes our gut feeling, following a certain direction within a certain discipline that we are in. And at some point we are lucky and we have some contribution, and it doesn't matter whether it's epsilon or 5 epsilon. As long as it's positive, we keep going. And the net result is sometimes we get transformative changes. And very much as we were talking earlier with Christy, I always remember one of our, the fellow who started off the National Academy of National Science Foundation, praising the pursuit of knowledge that at the beginning may look useless, but at the end we get some great discoveries, and many of these discoveries came out from academic cycles, academic environments. So returning back how I direct my group, my students think that they're learning from me, but actually it's the other way around. So I try to expose my students and colleagues to ideas, things that bother me, things that I paid attention to. Sometimes I direct their ways, things I didn't understand, and through discussions, somehow we come to the next level. And I was also very fortunate over the years to have great colleagues and mentors and heroes in our field that I learned a lot, and it's this freshness of the mind that you pursue something, you try to explain it, that is most important. And it is great fun to be in academic environment, and whether we pursue an academic environment or we go to industry, it's always very important in these years that we're here to understand that it's not a vocation school. The university is a place where we learn, and we learn how to learn, because what we are going to be doing tomorrow may not be exactly what we're doing today. So you have to take, those of you that are following different routes, take it kind of in an open-ended direction, sort of, and get this opportunity to challenge yourselves with new ideas, sometimes for the sake of learning, and it will be very useful in the long run. So with that, I think I probably should turn to the topic. I have a lot of material to cover, but I'll try to explain it. There is some mathematics. I'm going to skim through this and try to explain the physics behind it. So what I'm going to talk about is something I consider a great success story that started several years back, and we're very fortunate to enter this field at some early stage, and we have some contributions. And the subject is thermodynamics and stochastic control. So thermodynamics is a very old subject, and it basically connects to almost every other direction in science, from gravitation to mechanics to almost everything. Thermodynamics has something to say. Of course, chemistry and so on. Another thing I want to say before I begin is that it's always important to realize that you are stepping on the shoulders of giants. And there were some early prophets in our field advocating stochastic control, like Jan Willems and Roger Brockett we discussed earlier, that I'm not going to mention much of their work, but there's a long transition from the physics community to what I'm going to talk to you today. And the transition was, in order to be able to understand thermodynamic transitions that take place in a finite amount of time, it took a very long time for the mathematics and the physics to come together. And this is what I'm going to talk to you about. So it's about finite-time thermodynamic transitions. The field starts almost 200 years ago with Carnot. The fellow in the middle is Gaspar Monge, has something to do with a subject in mathematics which is called optimal mass transport, and the other one is Boltzmann. So entropy and optimal transport sometimes come together, and the paradigm of Newton, where you have a particle that moves under some action of forces, transitions to laws that govern collections of particles, Avogadro number of particles. And the subject impacts many things, many fields: biology, quantum mechanics, computer science. I'm not going to talk about all of this, but I want to give you a little bit of the gist of it. It interlinks many themes. So 200 years of mathematics, Gaspar Monge, and later on Kantorovich, and here you have a Kantorovich Institute, introduced a set of problems that are grouped together under the title optimal transport. Optimal transport is something very simple. You have some dirt here, and you want to move it from here to there. And you pay according to how much you move every pebble. And what is the optimal way of moving? Which pebble goes to where? That gives you a very nice geometry. There is another subject, large deviation theory, I'm not going to talk very much about. And then 120 years ago, there was thermodynamics. Thermodynamics was invented at the beginning to understand the efficiency of steam engines. And then we have the Carnot engines and the Carnot efficiency. But it took a very long time before we managed to understand a little bit the transitions when they're taking place very fast. Carnot's deep inside was that you transition very slowly. So you almost at equilibrium. And in the mid-20th century, when there was non-equilibrium thermodynamics, it was also about slow transitions. And 40 years ago, we see the need to understand the thermodynamic processes that take place inside the cells. For example, transcription, mRNA transcriptions, ATP phase machines, flagellus motors that I'm going to talk a little bit about. So the key buzzword for what you're going to see, and which is the high point of the talk later on, is the word anisotropy and gradients. So let me begin in earnest here, talk to you about optimal transport. Optimal transport is about moving mass from initial position to a final position with a transportation map. So this was a problem that started with Gaspar Monge. Kantorovich reformulated it and introduced linear programming to solve this problem. And basically, in order to relate what particle goes from where to where, he tried to put them in different directions here and look for a joint distribution and solve a problem that at the end of the day give you a transportation plan. So you go from here to there. So I'll explain a little bit this. So this is Gaspar Monge's formulation of the problem. You want to minimize a transportation cost. You move from X to Y under the transport map, and this is your penalty. And you sum up how much mass you move. And you want to find the optimal transport map. This gives you a distance between this distribution and this distribution, which we call the Wasserstein distance. So you have two masses here, mu and nu, and this gives you a metric. That metric is extremely important. It's very much like the Euclidean metric. If I give you 2 points and you say, what's the distance between them? You have the Euclidean metric. Now, you don't have a point and another point. The point is a whole distribution. So this is the Kantorovich formulation, which says that I'm going to look at correspondence between X and Y, and I look for a joint distribution in a product space that minimizes this distance. And for reasons that take us a little bit too far, this is a much easier problem to solve. And he invented, in fact, linear programming in order to solve this problem. So I have probably to move a little bit on this. This is somewhat technical. But when you solve the Kantorovich problem, you end up having a solution where the coupling, where is the mass transported, lives on this transportation plan. So in this way, you can devise a transportation scheduling that moves the mass along from the beginning to end. These are optimization problems. Now, this is another very, again, the first 3-4 slides are a little bit technical on optimal transport, and will give you just the gist of the mathematics behind it. Now, when you move in a Euclidean sense from X to Y, the distance between 2 points, you can write it as the integral over 0,1 over time of the square of the velocity of a particle that is going to be moving from the beginning to end. This is a trivial high school type of exercise that if you want to go from X to Y, the optimal way is you decide how far you go, you fix your velocity, and you pursue it. Now, a consequence of this is that you rewrite this distance as an integral of a velocity field squared times some mass. And here you have a continuity equation that simply you move some initial distribution to a final distribution. This was an eye-opening reformulation of the transportation problem because it shows that this metric on distributions becomes an action integral in the style of classical physics. So you have here average kinetic energy and you minimize over time. And that gives you the dynamics of the flow that optimizes the transport. So if all of the things I said before seem complicated, this is one of the things you can retain. So this is an action integral. And here are another two slides that I'm going to go somewhat quickly. Here you have the continuity equation that tells you the density, the change in the density depends on the divergence of rho times some velocity field. In this way, changes in the density can be correspond to velocity fields that are optimal. And the changes in the density are mapped to a velocity field through a certain equation, and this allows you to take inner product in the space of perturbations and to define a inner product, a dot product if you like, which is consistent with the interpretation of the transport as a kinetic energy, average kinetic energy. That gives you some beautiful calculus. This is some new type of calculus called Otto calculus. This is very much kind of analogous to the calculus that we have in Euclidean spaces, but now it's on spaces of densities. Okay? And the beautiful result, which with that I'm closing this introductory thing, is a result that goes back about 20 years, that when you have rho is a density, so think of it as a temperature of some material here, a temperature field of some material. And then you ask the question, what is the gradient of the entropy? Entropy represents sort of the spread, the uniformity. Entropy is a functional, so if I have a temperature profile, I can compute the entropy of this distribution. So if you use the metric of the optimal transport to find the gradient, and you try to see in which direction the gradient is increasing the fastest, the entropy increases the fastest, you find out that this is the heat equation. So this is quite a remarkable result that connects optimal transport to information to physics. The physics is the heat equation. Optimal transport is this weird symbol here that says you take the gradient with respect to a certain metric. And information is the symbol S, which is the Shannon entropy. The Shannon entropy is integral rho log rho, and it has a meaning of information. So this thing here somehow tells you that optimal mass transport in stochastic enters into the realm of thermodynamics and dissipation. Okay? So let's leave this introductory picture in the background. The only thing you need to remember is that the points now gave way to distributions. The points in this big space are distributions, and in this space we can take derivatives, gradients, and we can do some calculus. So we're going to talk about stochastic thermodynamics. Thermodynamics taking place at the level of individual particles, and we're going to be moving far from equilibrium and looking at finite-time transitions. And there's a lot of applications that will benefit from insights that this new theory allow you to draw. For example, the thing that we have in mind is to try to understand things like the flagellar motors. These are biological engines that rotate very fast. So you have a bacterium that has this flagella, and this is really an engine. So this thing rotates fast, and the bacterium can move even 17 body lengths per second. So it's absolutely remarkable. They rotate at 3,000 RPM. And how do they do it? So I'll come back to this after I give you a few slides of sort of background, how you model thermodynamic engines, and how do we quantify power, efficiency, and work production. And optimal mass transport will be the key to this. So this is a fairly elementary picture that we've known for almost 100 years since Einstein. It's a model of diffusion. So here you have a particle which diffuses when bombarded with smaller particles that represent a heat bath. It's a model for some mesoscopic systems that live inside some environment and sort of drift around, very much like the model that explains Brown's observations when he first observed Brownian diffusion. So he looked under the microscope, pollen inside some liquid, and the pollens kept jumping around. Initially they thought that this was alive, but it was not alive. It was sort of like a piece of molecule, a little bit bigger than the molecules of water, and the molecules of water bombard into it, and then it drifts around. So that's our sort of principal model. And Einstein came along and explained it in 1905, and he wrote down this remarkable relationship here with the diffusion coefficient depends on the diffusion balances drift current due to various forces that it's experiencing. So in other words, this particle, if you leave it alone, is going to diffuse under the influence of bombardment by smaller particles. But if you tether it and you start trying to pull it, there is going to be a force from headwind. So Einstein explained how the two things balance each other. And all these expressions here, the diffusion coefficient, Kb is some constant due to Boltzmann, and T is some temperature. The temperature relates to the fluctuations that this particle experiences, how much it's bombarded, because it sits inside a heat bath. And there is a simple model that we use to understand this, which is basically Newtonian mechanics. So you have that the change in position is velocity times dt. So this simply says that x dot is the velocity. Now this one says that the acceleration m times the derivative of the acceleration is equal to some forces that are being acted upon by some potential. This u is a potential, and this is the gradient of a potential that gives you a force. There is some friction, and there is some thermal excitation. This is the Einstein relationship. You don't need to worry about that. And this is Brownian noise. This is like models the fluctuations. The dB is some changes in sort of forcing, if you like. Now, a simpler model is if the mass is extremely small, so this becomes 0, and the dx here equal vdt enters in this spot, and we have what we call overdamped dynamics. From now on, this is what we're going to have. This is our model. In other words, we neglect inertial effects. The particles very, very quickly move to different position, and somehow the time constant is such that we can neglect the accelerations. So this is the basic model. Dx depends on the forcing and the stochastic excitation. So I think I may have a little bit, again, I don't know if I will go through at a relatively high level of the math, but then you will see how all of this comes together. So this expression here that we've written represents of individual particles. So x is the position of one particle. The position of the particle and some strength of the potential allows us to control how we're pushing it. And this thing here is stochastic excitation. This is called a stochastic differential equation. When we look at collectively a number of particles, this is described by a a partial differential equation, which tells us that the density of the particles, this is an ensemble, changes according to this equation where you have a gradient of rho times the velocity field, a velocity field. And this velocity field takes this expression. So it depends on the forces that acted upon it, as well as some forces because that are due to the different gradients of the density. Okay? So this is called the Fokker-Planck equation and describes how collectively a collection of particles move. Now, these are two slides that give you basically the first and second law of thermodynamics. The first law of thermodynamics tells you that if you have a particle inside a potential U, the change in the potential is the change of the internal energy. And if you take the derivative and you express it in terms of how it is affected by the changes in the potential, which you are going to do, and how the position of the particle interacts with the, here I have, fluctuations in the position of the particle, you can discriminate and say that this is due to heat interaction with the heat bath, and this is interaction with the potential, so this represents work. This is not so easy to understand, but at the level of individual particle, you have a particle which sits inside the potential. If you lift the potential, you're doing work to it. And the particle, by jittering around here, interacts also with the heat bath. So this splits these two things, and one of them has to do with heat exchange between the particle and the heat bath, and the other interaction of work between the particle and the potential. So that's what this equation here means. And when you integrate this, you get at the level of the ensemble, you can quantify the work and the heat. And when you put all of this together, you have that the total change in the internal energy is due to the work and the heat that is exchanged between the particle and the environment, and the potential in the particle. So now there is another side to this, which in physics it's if you have a density here, rho of the ensemble, the entropy of the ensemble is the expected value of the logarithm of rho. And this in some ways ties to information, but it's a little bit deeper than that. There is a quantity you can define, it's called the free energy, and this is the internal energy minus Kb times T, which is the temperature, times the entropy. And this represents the amount of work you can get out of the ensemble if you manipulate the potential and you keep the temperature constant. This is the free energy. So if you take the derivative of the free energy, then you can and you integrate from moving from some initial density to a final density, the work that you get out is, using the previous formulas, is the change in the free energy plus a certain expression. So this actually is central to what we're going to do. So the free energy, if you move from some initial distribution to another one under the effect of some potential, you can go back. But in the process of doing that, you may create some dissipation. These are losses that you cannot recover. And you can see it here because this quantity here is positive. If you recognize this is nothing more than the Wasserstein distance, because this is a velocity integrated against the density. So, and this is basically the second law of thermodynamics. So now, pictorially, the way to see it is, and here we can take a little bit of a break to understand this, is you have a bimodal potential, and you have particles that are concentrated either on this side or on that side, And by shaping the potential, you can make it unimodal. In the process, each particle will obey this equation, and the totality will obey the Fokker-Planck equation. If you do the calculations and you try to see how much work do you need to do in order to move the bimodal distribution to the unimodal, you have to reshape the potential to herd the particles from the beginning distribution to the final. And if you do that, you see that the work you do is equal to the change of the free energy, and the free energy only depends on the shape of the densities. Okay? Plus a certain quantity here, which is extremely important, and this is the length of the curve in the optimal transport metric square divided by the duration. So if it takes you an infinite amount of time to go from here to there, this thing here becomes 0. And the transition is quasi-static. So the work is equal to a change in the free energy. Otherwise, this represents wasted work. So that gives you, for the first time, some sort of quantification of how much wasted effort you're going to have to put to move in finite time. Here is, for example, a repeat of this relating to something that puzzled physicists for a long time. The question was, what is the cost of computation? If I do a computation, how much energy I'm going to use? Let's say I compute something. It turns out, in order to do the computation, you can do it with some sort of orthogonal transformations, unitary transformations. You don't waste any energy, but the energy you waste is when you erase bits, when you clear the memory of the computer. Okay? So theoretically, the resolution to the question of how much energy I'm going to be spending to do a computation was understood when it was realized that you have to waste energy when you want to clear the previous memory. You erase the bits. And this was basically the insight brought in by Landauer about 40, 50 years ago. So the erasure of a bit means that if you have a particle which is here or here, so you have a 0 or a 1, you're going to reshape your potential to make sure that it is in the same spot. So you lose memory of what happened before. So basically you go from a bimodal distribution to a unimodal distribution. And Landauer's bound was that the work that you have to spend is equal to the change in the free energy. And if you allow infinite amount of time, this is how much you're going to spend. It depends on the temperature of the heat bath that you're sitting. Imagine that you have a switch, and the switch can be either up or down. But you are inside a heat bath. I mean, everything is shaking. So randomly it can switch back and forth. That is extremely important in this whole process. You're not going to do it in a zero temperature environment. Okay? And this exactly gives you the amount of work you have to spend. And if you want to do it in a finite amount of time, you have to have some extra dissipation, which is exactly what I showed you in the previous slide. Okay, now two more things, and then we'll go to the most exciting twist to all this. Okay? Bear with me. I know there's some mathematics in the background. Okay. So here is a model of a Carnot engine. So what is a Carnot engine? You have a cylinder which you bring in contact with a hot heat bath, and then because it's heated, the gas inside is pushing on the pistons. So you allow the piston to move and you get some work out. Then you bring it in contact with a cold heat bath. Now the molecules don't push anymore because the pressure goes down. So you can afford to waste a little bit of work to push the piston back. Right? And then you bring it back in contact with a hot heat bath, and you repeat. So this is a model of a Carnot engine using exactly the model that we talked about before for guiding particles with a potential in a certain temperature when they are immersed in a heat bath of a certain temperature. The temperature will change. So here there is a hot temperature, T sub h, and the particles sit nicely and comfortably inside this potential. That's a quadratic potential. Because they sit inside this potential in some temperature, they position themselves to have a distribution which is like a Gaussian distribution here. They have some randomness, so they're going to be somewhere on the x-axis. Now, but they're pushing against the potential intuitively. So if you act on it and you open up the potential is very much like a spring constant. So each particle is tethered to the center with a spring. If you relax the spring constant, they're just going to move out because they're pushing it on the average. It's almost like the piston being pushed out. And you get some work out of this. So in this part of the cycle where the ensemble, here is an ensemble of particles inside this potential. When the potential changes from 0 to t and opens up, we're going to get some work out. And you can compute the work. You can just write some integrals and just do it. Okay, it's not entirely trivial, but you can do it. Then you, without much delay, you switch here to a different temperature, and instantaneously you open up the potential. The particles don't have any time to move, so there's no work done. And again, if you stay there, they will sit comfortably in this widened potential because the temperature is lower. But what you do is you just start pushing the potential back, and you bring them back to the beginning distribution. But you do this under a temperature which is colder. So you're using some work here, and you're gaining some work there, but you're gaining more work here than you're using here. And you can go through the cycle and do the calculation and the budget. How much work you get, how much you put in. So if you do that, you can write that the change in the free energy as you go around the cycle, because you return to the beginning distribution, if you integrate over time, is going to be 0. And then you're going to have how much work you're going to get out minus how much work is due to irreversible losses. And after you do all this, you can compute, for example, the efficiency of your engine. So the engine is simply a potential that retains the particles, very much like a piston retains molecules inside a cylinder, and you open and close. So if you do it in an infinite amount of time, so these t's here are the times it takes you to go horizontally, down, up, and so on. If these are infinity, this whole thing disappears. And then you get basically Carnot efficiency, because this is the change in some entropy. It cancels, and you get what's called Carnot efficiency. This was a brilliant formula that Carnot did almost in a back of an envelope computation. Carnot, he was a brilliant engineer. He basically thought of this idea of going quasi-statically, infinite amount of time. He came up with this formula. He published a monograph with his own money, printed about 150 copies. And this manuscript would have been lost, except that one copy ended up in Clausius' desk, and somehow the rest is history. And Carnot died at a very young age. I think he was 35 years old, out of plague or some sort of disease. Maybe, I forget now, maybe tuberculosis. I don't remember. Okay? And this formula basically dominated science ever since. This is called Carnot efficiency. So if you take a lot of time to go through the cycle, the efficiency is this much, and this is the holy grail. Now, if you do it in finite time, it depends on the shape of the potential and the shape of the distributions at the beginning and at the end of the cycle, and the time it takes you to do that. And this degradation is due to the cost of transporting from one to the other. So all of a sudden, we have the tools of computing how much we lose if we go in finite time. And you can compute the efficiency and you can compute the power delivered, because you can compute how much energy you get out of a cycle, and you have the time of the cycle, and you can compute all that. So for fixed TC, for you can play different things and try to see for arbitrary temperature profiles how you optimize power over protocol and terminal states. And you can do a lot of different things trying to find the limits of how much you can do out of this protocol. The protocol is this Carnot scheme where you hit and then you cool. You hit and then you cool. And that's a cycle. But that's not how nature works. In our body there are engines. There are cells that move about. They don't have valves to switch. They don't have a combustion engine. And we don't have two heat baths that we alternate. There's no such timing. So how do we move about? How do cells, how do bacteria are powered? They are powered because of anisotropy. Why is there life on Earth? There's life on Earth because we have the 6,000 Kelvin photons coming from the sun, and then we have the cold starry sky to throw them out again at 300 kelvins. That's how we emit them back, because that's the temperature, average temperature on the planet. So we are there to basically suction some work out of this negentropy, some people say. So there is a gradient. So engines work with a gradient. There is a gradient. There is an anisotropy. You look here, imagine what will happen if this wall was very hot and this wall is cold. What you're going to see happen inside this room, there will be a little tornado. There will be instability and the air will be rotating, taking heat from the hot wall and transferring it to the cold wall. So this anisotropy creates motion. And out of this motion, we can get work out, this circulatory motion. That's exactly what we're going to see in the next few slides. So how do we harvest energy in nature? Metabolic processes, biomolecular processes, and so forth. The key is we have systems far from equilibrium. We have thermal gradients, we have chemical gradients. Most of the times I'll talk about temperature gradients, but it's the equivalent. So here is the latter part of the talk, which is the most exciting. We're going to see how an engine can work out of anisotropy. So what you see over here is a electrical system. It's called the Brownian gyrator, and you have two resistors. One of them is heated, and one of them is colder. Maybe somewhere in physics you have seen that if you hit a resistor, there's going to be some fluctuations of current in there. This is called Nyquist-Johnson noise. And if you hit it more, there's more fluctuation. And then you have here some capacitors. So if you let this system alone, what is going to happen is you're going to see some fluctuations of current that on the average is going to start rotating between those components. So it's almost like the example that we had before. You have a particle in a heat bath that is fluctuating, but on the average keeps rotating. It goes in contact with a hot wall, because of the geometry, rotates back to the cold wall, and so on. So this is a model for it, and you don't need to read this very carefully. You have a direction that corresponds to the hot direction, that relates to the temperature, and this is the cold one. So if you have the particle in here, it's going to be moving around. Now it interacts with a potential, which you have control over, and these are the two heat baths, the different temperatures. And the potential here is like a big spring constant. It has two spring constants. This K represents spring constants. It's like a matrix. It's sitting in the middle. Okay? Think of them, the way to think about this, think of a particle being sprung in these two walls with some two springs, and then the other walls with two other springs. So if you shake the springs, this is going to be bouncing around. If the geometry is right, you're going to see that it bounces around. It has a directionality. And it's this directionality that we're going to tap on and get work out. So this is a little bit too technical, and I'm going to go quickly through this. So the position in the x and the y coordinates can be encapsulated in some covariance matrix. And the covariant matrix, for those of you who have taken linear systems, graduate level linear systems, obeys what we call a Lyapunov equation. So here is the covariance, here's the derivative of the covariance. That's a linear equation in K. And here is the temperature. The temperature now is a matrix because we have two temperatures. So we don't have the Carnot setting where we have the hot and the cold. We have both of them at the same time. They're just coming in different directions, and they create this vortex. So this is the temperature, and it's diagonal, and it has the hot here and the cold there. And you can specify the K so that you get work out of it. Now, we can get rid of the K and write it as a function of the covariance and its derivative. Trust me on this. We want fewer parameters, right? So you can do that. So, and we view now the engine as moving in some sort of a manifold of distributions. These are Gaussian distributions, and they are characterized by what? They are covariance. They are centered at the origin, and they are basically a Gaussian distribution that is stretched this way, and then the next minute it's stretched that way, and then it's stretched this way. So we are going to be shaping them around the origin and turning it. They have a natural tendency of turning around because if you look at the particles, if you look at this as a stationary, so you just leave it alone, you don't do anything to it, you're going to see that the charges here, which are Q1 and Q2, give you a position in space, and the density stays put. But if you take individual Q1s and Q2s as a point in there, and you think of them as a particle, there is going to be a probability current. So it's going to be flowing around. You see some anisotropy creates a vortex. So now the covariance is a little bit of a complicated object. It's a matrix. So we're going to simplify it. Again, you have to take my word of it. All the math is here. You can write it as a orthogonal matrix with some theta, and then some matrix of the eigenvalues. The two eigenvalues, we simplify a little bit, so we take the determinant of sigma to be constant. That simplifies the analysis, and there's no loss in generality. So we have two eigenvalues that give you the squashing. Is the covariance, is the Gaussian spread this way or that way? We take the ratio of those two, the logarithm, and we call it r. And we take this theta and we call it phi, and this r and phi represent the covariance. And as the symbols suggest, we are going to use a polar coordinate to represent the covariance with a point in space. That's a representation. So every point in space represents a covariance, which represents the Gaussian distribution. If it is squashed this way, there's going to be a different r and theta. Okay? This is the picture that we need to have in mind. So if we're sitting at the origin, the ratio of the eigenvalues is 1, so the logarithm is 0, and we have a Gaussian which is isotropic. If we move here, then one of the eigenvalues is bigger than the other, so it's squashed. These are level curves of a Gaussian. They're all centered at the origin, but pictorially we are going to be shaping them, squashing this way and that way, and you will see how this can be done automatically. And then we can rotate and then squash back. And this is going to be a cycle. So here you see how the Gaussian looks when we're somewhere there. Okay, so and this really represents a number of particles inside the retaining potential, but it could be just an individual particle, but and describing the probability of it. So here this slide is just too busy, but the exchange of the heat between the particle and the potential and the environment, if you do the computations, gives you two things. One of them which is quadratic in the velocity here, and one which is linear in the velocity. So if you go extremely slowly, this one disappears. And it's basically all the dissipative losses. And this one is the quasi-static loss, quasi-static exchange of heat, which is really the work that you can exchange with a heat bath. So to make the long story short, we explore trajectories inside, in this representation of the densities. And what we observe is that the quasi-static heat is the heat that the system exchanges with a heat bath, okay, turns out to be an area integral over the domain which you are traversing. So you can have any trajectory here, and depending on the directionality, you are going to suck heat from the heat bath, one of them, and then spit out some to the other, and in the meantime you will keep some for yourself. The length of the trajectory here represents dissipative losses. Again, this is kind of a busy slide, but the bottom line is that if you look at this picture, every point of this represents a Gaussian distribution with some tilt towards the different axes and some squashing. Okay? And any trajectory here represents how your potential is shifting this Gaussians around. The area integral represents work that you get out, and the length of the curve represents dissipative forces. So you need to maximize the area for a certain amount of losses. And you get what's called isoperimetric inequalities that can bound the maximum amount of work or efficiency you can get out of this. So you can get the work out is basically the area minus some coefficient here, which is a physical constant, times the length square. This area and length are areas and length in the space of densities with respect to the metric that we were talking earlier on. You can think of it as Euclidean, but they're not. They're just something a little bit bigger. Okay? And then you can compute efficiency, and you can see the maximal efficiency you can get out of a certain anisotropic field. So, you have to decide the length of your cycle, and if you go faster and faster and faster, sometimes if you go around the cycle too fast, you waste more energy than you get out. And then somehow there is no solution after that. So you can actually quantify all of this. Now, let me take the last few slides to get to a physical incarnation of what I told you. All of this is kind of mathematics. So you say, okay, fine, everything you told me is okay, you have all this math, can you actually do an engine out of it? So here, in order to make an engine out of this, what we need to do is we need to change the capacitors, the capacitances. And we can have them time varying because the capacitors dictate what the potential is. So here's how we're going to do it. So you have a dielectric material that it is pulled in and out. So those of you that remember your electrostatics, if you have a capacitor and you increase the voltage and you have a dielectric material that is sticking out, the tendency is for the dielectric material to be sucked back in again. So you're going to get torques out of the different capacitors depending on their voltages. And the voltages are not constant, they're fluctuating. But on the average, you create a torque. And the torque integrated gives you some, so here are the expressions. This part is the system of the Brownian gyrator that I told you earlier. A second order system that is excited by the stochastic excitation of the heat baths. And this thing here is an inertia of a wheel which experiences a torque out of the capacitors, and there is some friction that is there to move some of the work out of the whole system. So you make an engine out of it. And you can actually show that there is limit cycle oscillations and that this engine actually can be a viable model for an engine that sucks energy out of this anisotropy. And then couple more slides and I'll finish. So what actually happens is the anisotropy creates the position of the electric material basically tilts a certain potential, and you have the stochastic particle fluctuating and then going down the potential, generating the torque that you can siphon out. A large-scale engine of a similar type, where the analysis for the maximum power and dissipation I don't think has been fully done, but it can be dealt with in a very similar manner, is the so-called Stirling engine. It's very, very similar. It's a large-scale engine. How many of you have seen Stirling engine? You can buy it for $50 from Amazon. This is not an advertising, because you can buy it from other places. You put it on your coffee cup, and all of a sudden this starts rotating. And there are no valves. There's basically a hot plate and a cold plate, and the circulation allows the pressure to keep generating a torque. It generates a torque, it's basically like a pendulum where you apply a torque. So if you don't do anything to it, it will stay there. And if you tip a little bit, it will just oscillate because there's a constant torque. But if you push it a little bit more, every time you go around a cycle, it will gain energy out of this and will keep rotating. That's exactly the same thing that we saw in the stochastic Brownian gyrator. And a very similar thing seems to be happening, though this has not been seen that way, but it presumably will be analyzed in some point in the near future in flagellar motors, where you have a gradient here of some chemical potential, and it creates a little torque in an ensemble of proteins that, if you look at it from above, it looks like a 6-cylinder engine, actually 11 or 13-cylinder engine. So there is chemical ion flow between those that create a little torque, and this torque is sustained. So you can actually see that if you have many such engines and you put them in parallel, you don't need the inertia in the middle for the contraption that I gave you in the previous slide. And you can prove that this is going to be, at least in theory, have a proof of concept that you can make an engine out of this. So presumably, many of the biological mechanisms are similar or close to that. And with this, I would like to close and say that I know I gave quite a few math formulas, but the thing that one can gain out of this is the following. So there is stochastic control, and the way we model fluctuations, which go back to Einstein. And we have these stochastic differential equations. They're not very difficult. They're just differential equations, except that one term is fluctuating, which is noise. So the particles jitter around. If they find themselves in some anisotropic field, they can have what the physicists call a non-equilibrium steady state. So if they are in non-equilibrium steady state, they just keep going around, taking heat from the hot heat bath and moving to the cold heat bath. But if we manipulate the potential and we allow this ensemble to rotate, either actively or autonomously, like I explained, you can get work out of it. And that was the whole point. And the Newtonian explanation for one particle gives way to Monge's explanation of a collection of particles, of uncertainties. And the geometry here, instead of having Euclidean geometry, you have the Wasserstein geometry, which is given by optimal mass transport. And instead of having Newton's equation, you have the Fokker-Planck and the Liouville equation. But you can still talk about gradients. It's just that it's in a bigger space. And in this whole thing, you have the transition from this geometry to being able to analyze at least some model engines. And with that, I would like to say that one more thing is that it's very interesting how very simple fundamental ideas, Einstein's idea of a particle that sits inside a heat bath and just jiggles around. You have optimal transport. Monge, so many years back, said you move masses, you move distributions, you get a new type of geometry, and all of this come together. And we have a new phase in finite transition thermodynamics. This is a new field. It's exciting because you can do things we couldn't do before, albeit for simple models. But we are going to go much further than that, hopefully. And this is the team that produced this work. And I would like to thank them very much. Olga, Amir, who sits here in the first row, and he was the heart and soul of the team. Rui and Yongxin. And with that, I would like to thank you for your attention.
Is the time scale for the maximum power extraction determined by some diffusion time or thermal inertia time?
It is dictated by those parameters which are chucked under they put in this mu that we had there, and this basically brings together all kinds of physical constants. So if you have that, and you can find out the max. Again, you have to iterate. You have to see how much time you have. You go around and you compute how much you get for this period and for the other period. And there is physical parameters enter into the mu, and the mu tells you exactly what the optimal is.
Thank you.
Other questions?
So I have a question about from a different perspective. So you consider two dynamics with different temperatures, hot and cold, right? Does it have in the long-term behavior of the cold dynamics?
Say that again.
Does it have to convergence of the cold temperature dynamics?
Cold temp.
I mean, in general, so in the Langevin dynamics with the cold temperature, the large beta converges very slowly. It's known in other fields. And if we consider two different dynamics with two different temperature and coupling them, does it have the convergence of the cold temperature dynamics?
Oh, you mean towards equilibrium? Yeah. But here we're not going to equilibrium, right? I mean, it depends, right? I mean, if you have these two temperatures and you have some ensemble that experiences both, and you don't do anything else, and the dynamics of the system are static, it's going to converge to this non-equilibrium steady state. And you're asking about the speed of convergence to equilibrium. Presumably it's going, again, I don't have it in my mind. It's probably going to be the coldest temperature dictates that. But here, if you want to build an engine, you don't go to non-equilibrium steady state. It's a state that keeps rotating. So you get a periodic non-equilibrium trajectory. And your question of how quickly you converge to this periodic non-equilibrium trajectory, I don't know the answer. But there must be an answer, I mean, how quickly. But we are just simply studying the periodic orbit, not how fast you get to that.
Any other questions? All right, well, thank you again.
Thank you very much.